Hey everybody, this is Mrs. Dinkelman, and this is the FRQ advice for Friday, February 17th, since I won't be here on the 16th. So we are going to do a differential equations free response, which is what we've just been learning, and there will probably be a slope field. We'll talk about drawing that curve on the slope field curve as well. I'm not sure these examples that Mr. Spain provided have that, but that's definitely something that could be on the test or the quiz on Friday. So just kind of phrasing wise, to me, there are a couple phrases that that you need to see here, and that's this general solution or particular solution. The particular solution is the one where you know the plus c value. I know on this one it's where we actually draw through the slope field. So we'll do that in a second as well. Again, particular solution, they'll give you some kind of value that you can find the plus c. When we still have a plus c, it's called a general solution. These are usually worth a lot of points. So this is just an example of what they'll be worth. So usually 1 point for separating properly. And then the antiderivatives are either 1 point for each side or 1 point for both. And then 1 point for having the plus c. And then using the initial condition, or the condition given is usually one that you get. And then 1 point finally for having the correct answer for the y equals at the end. And these are all just the separate problems. So let's look through the examples, and I'll kind of talk through. This is an example of one where they actually ask you to do a slope field. So on A, it says, on the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. So you can see here that there's 1, 2, 3, 4, 5, 6. What I tend to do, especially when there's x's and y's, is do that in a chart just to keep track. So like for this point right here, it's 0, 0. So we would get 0 over -1, which is 0. So you can see that whoever did this one, this is the answer, has a nice horizontal line there. And then at 2, 0, we also get 0, and so on. So we just would plug in those points to make sure that we have those correct. If they ask us, this one's a little bit tricky. It would be hard to draw a solution curve just because there's not enough tick marks on here. But remember, sometimes they do ask us to draw the solution curve. So maybe this one kind of goes like this, maybe. Just remember that when you draw a curve, it should always be a function. So we would never want something that's sideways like this. We would never want to include the top and the bottom. We would just do the one part that they're asking for. Okay, on part B, the phrasing I see there is that they're asking for a particular solution. Oh, not yet. I'm going to keep reading. So this one also says particular solution, which is why I was thinking. But this one, they say write an equation for the line tangent and use it as an approximate. So this is a lot like, I can't remember what problem it was in the assignment that we just talked about today, actually. So on this one, because it says tangent line, I hope you'll see that line tangent and just draw a tangent line, or not draw one, but write one. So we know that the point is 2, 3, and the dy dx, the slope is given up here. So our slope is going to be plug in the 3 for y, and then the 2 for x. So we just get 9. So we would do y equals slope, x minus the x coordinate plus the y coordinate. You have to pardon my voice in talking. And then the next thing we would do, my notation that I prefer, is that f of 2.1 is approximately, and then we would plug the 2.1 into that tangent line. Okay, part C is the particular solution. Okay, I tried to put in a cough drop. We'll see if that helps. Notice how many points part C is worth. So again, really quick here, that separating the variables properly, the antiderivative on each side, having the plus c, and using the initial condition to find it, and then finally just solving for y. So this is basically saying that the max points you can get with no constant, so not having a plus c, is 3. And if you don't separate, you can't do any of it. So even if you put a random plus c, they would not give you any points for it. So I know that the answer is over here, but let's go ahead and just kind of do the work so you can see. So again, we're going to separate the variables. I'm going to call that a 1 on top. We probably want to write this as y to the negative 2. That's what would make sense in my mind before we take the antiderivative. So we're going to add 1 to the exponent, divide by the new exponent. This is a natural log because it's an x to the 1. Now what I tend to do on here is I use the absolute values until I know I don't need them. I'm going to rewrite this one more time because I don't really like that y to the negative 1 on the bottom. I want it on the bottom instead of the negative 1 on the top. Okay, so we have this condition that we have a 2, 3. So right here, I'd know that I didn't need the absolute values, so I'm kind of okay to drop them on my next kind of steps. Natural log of 1 is 0, so we have our c value is negative 1/3. I'm sorry, I was getting off the page there. Let's go back and look at that. So add 1 to the exponent, divide by the new exponent. This one's a natural log because it's an x to the 1. And then I just changed that because I didn't like the negative exponent, so I rewrote that. So now I know my c is negative 1/3. So I'm going to kind of come from this one. So I know that negative 1 over y is equal to natural log of x minus 1 minus 1/3. And just by the way, just in case any of Mr. Spain's students are listening to this, I tend to find the c value right away and then solve for y. I know Mr. Spain does it slightly differently, and it doesn't really matter. Some problems are easier one way versus the other. All right, I think I'm going to multiply both sides by y here. So I'll just have negative 1 is all this mess times y. That way I can solve for y pretty easily. Now you can see the way I did mine is a little bit different than they have. They have switched on the bottom instead of a negative 1 on the top, which is the same as what I have. Okay. Now sometimes they will give us a kind of a differential equation in context. And the trick on this one, usually is students have a hard time with the variables. So if you want to change things, you can. If it makes more sense for you to call this dy dx equals 1/25 times y minus 300, that's fine. You just need to know that that w really is like the y coordinate. So that's what makes this a little bit tricky. Okay, so let's look at A. Use the tangent line to approximate. So let's just start with the writing the tangent line and then we'll do the approximate. So at t is 0. So when t is 0, let's see what they give us, some information about, okay, so a landfill contains 1,400 tons. So our point is 0, 1,400. The other strange thing here is that, again, t is 0, but when I'm looking at my derivative to find my slope, then I need w, not t. So again, w of 0 is this 1,400. So I would have to go 1/25 times 1,400 minus 300. And then we would have to divide that through. So that looks like that is 44. I'm going to cheat a little bit on that one, but we would have to do that division. So our slope is 44. So we would go y equals slope x minus the x coordinate plus the y coordinate. And then they're telling us here to plug in the 1/4. So we should be w of 1/4 is approximately 44 times 1/4 plus 140. So I'll let you finish that one out. Sorry, I missed a 0 on that one. It's 1,400. Okay, part B, find the second derivative, and then we will kind of keep reading the question because there's more to it. Now, this is an implicit problem. Again, if you were to rewrite this in y's and x's, you might notice a little better that it is an implicit problem. 300. I keep trying to drop that last 0. So I just changed this to dy dx, and so the w would then turn to y. So this is definitely implicit because of the way that the y is there instead of an x. So I think I would take this one step further before I took the second derivative. So the second derivative here would be 1/25 dy. So my students, if you remember, there's that extra step in the second derivative where we have to go divide by dx. So I would say my answer is 1/25 times the dy dx that we had earlier. Well, that's just this that they gave us, so let's call that whatever that number is. Okay, so that would be the second derivative, but notice when you come down here and look at the answer, they're going to have it back into w's, and they've multiplied out a little bit, but that's what that is. It's an implicit problem, so there's their implicit right there. Okay, now is it an underestimate or overestimate, that tangent line? So we have to know whether this is going to be a positive or negative second derivative to know about concavity. So back here, if I plug that 1400 in there, I'm going to get a positive number. So it's saying here that the second derivative is positive, which means we're concave up. And if we drew a tangent line on something that was concave up, it would definitely be under. So that's how they get underestimate for that one. Okay, so C, here's that particular solution phrasing where I have to separate. And so I want to make sure I have the variables on the correct side. So kind of working from here, and then we'll kind of come down to look at that. I want this w minus 300 to be over on this left-hand side with that dw. I'm going to leave the 1/25. My advice is always leave as much as possible over on that other side as you can. And so that's the separation part. And now we would integrate. So that's a w to the first, which definitely means that's a natural log. And then over here, that's just a constant, so that must be a 1/25 t plus c. Okay, so then we're going to go with this information that they gave us to find the plus c. So it'll be ln of 1100, and the time is 0, so that's our c. Now, to be really honest, you don't have to have this completely simplified the way they would have it on the AP exam. So you're going to see that they have it in a really nice form, and I'll kind of talk you through where we could not worry about simplifying a little bit. I should have probably just changed these to parentheses because I noticed earlier when I plugged in the 1400, I didn't really need those absolute value bars, and obviously for the 1100, I don't really need them either. So I do need to E both sides here. When I E both sides, it'll get rid of that natural log on the left, and I'm going to have E to all that mess. So really there's only one more thing to do, which is to add 300 to both sides, and then I could technically be done with this problem. I am going to talk about how they kept going in case you're interested in it. That's an 1100. 1100. Pretend that says 1100 in there. Okay, so this answer would be totally fine because you have done what they asked you to. You've solved for W. You just haven't necessarily done this log rule right here and simplified, and they don't care about that. So if you want to know how they got what they have, they split this up. So remember, it's going to be e to the 1/25 t times e to the ln of 1100. Man, I'm really struggling writing all those. So the e and the ln cancel. And then you can see down here, that's why the 1100 ends up in the front of or times that e to the 1/25 t. Okay, the last one is similar to this one. I'm going to see if I can go grab a different one. So this one was called the potato problem. I remember the students really hating this. Same issue with this one as the last one, and that's the variables. So again, if it's helpful right here on this line, instead of dh dt, if you want to call it dy dx or dy dt, I'll go with x's, that's what we're normally used to. Then I want you to notice that that is a y right there because we changed the h to a y. So this is still an implicit problem. You can tell here they're going to ask us for the second derivative, so we're going to have to do that implicitly with the dy. And then this one was not the one that we separate. We go down and separate this one. So I'm going to skip down to C and go ahead and separate or separate that one. And then we'll be done. So notice on this one, again, if you want to change the G to a Y, if that's helpful, please do that. But the separate part is going to be, I need this stuff with the G over on the left-hand side. And I'm going to leave the negative with the dt. This is not a natural log. Had a lot of students on this problem be like, oh, natural log, it's a g to the 1. It's not really. So it's probably going to be helpful for you to rewrite that as to the negative 2/3 power, so that when you integrate, luckily the derivative of the inside's a 1, so no chain rule issue here, but I have to add 1 to the exponent, divide by the new exponent. Remember, I don't really want to do that. Divide by 1/3. And this is just negative t, or negative x, depending on if you switched your variables, plus c. Okay, what's our initial condition is that this g of 0 is 91. So I'll plug in the 91 and the 0. So there's our c value. And I guess that turns out to be a nice number. I'm just kind of cheating off of that. So the c, that's okay. They say I get 12 out of that one, so I'm going to just trust them for a minute. So I'm going to go back up to this one and rewrite it. Now it does say that we want to solve for g of t. So make an expression for g of t, and then we'll plug in the number. So we want to try to isolate g. So let's divide everybody by 3 first. And then we would have to cube everybody. And this whole thing gets cubed separate. I can't separate them. It's kind of all together there. So I would get g equals that stuff cubed plus 27. And then the final thing is it's your job to plug in the 3. So now plug a 3 in for time. And that's how they get their final answer. So this one, notice, is slightly different. Yes, a point for separating, but just the antiderivatives, both of them, you have to have both of them right to get that point. Did I have a plus c and use the initial? Did I solve for g? And then the final one is, I guess this one has g and t, so that means I don't have to solve for g yet, but I have to solve for g and find what's happening at 3 to get that point. Okay, I think that's all my voice can handle for the day. Just some advice on the FRQ. So quick reminder about the variables, that's kind of what those two are. And then last, about that slope-field one, remember if you have to draw a solution curve, which you'll probably have to do on Friday, you want to make sure that that solution curve is a function. So like if you look back at the assignment, there's a few where you have to do that, like number 3B, there's a bunch of them you have to draw. So if you want to look at that in your workbook, you can.